Hi, this is Remembering the Past, the show where we talk about people who've died recently who've had a profound effect on our history, our society, or our culture. And in our ongoing series on Nobel Prize winners, tonight we're going to talk about James Cronin, who died recently at the age of 84. James Cronin was a nice Irish boy from Chicago, and he won the Nobel Prize in Physics in 1980. He won a half prize along with Val Fitch, whose podcast we did a year ago. They were particle physicists, and they won the Nobel Prize for the discovery of matter-antimatter asymmetry, also known as charged particle or CP asymmetry. Basically, for a long time, physicists assumed that various symmetries characterized nature, and in a kind of mirror world where right and left were reversed and matter was replaced by antimatter, the same physical laws would apply. In the mid-60s, Cronin and Fitch discovered that the matter-antimatter asymmetry is violated when a particle called the neutral K-meson decays, and their experiment also proved that asymmetry does not apply during time reversal. That is, reactions going backward in time are not identical to those going forward, and this had profound implications in cosmology and the creation of the universe. Look, I didn't do such a great job with it with Val Fitch. You can listen to that podcast and see how I messed it up. So today, with James Cronin, rather than listen to me mangle the arcane details of particle physics, we're going to listen to him tell his story, and he will allude to the experiments that won them the Nobel Prize. Here he talks about his early education.
I was always interested in science, good in mathematics, had a great physics teacher in high school, although I think I would have done physics anyway. Actually, I was interested more in engineering. My dad, who was a professor of classical languages, said, well, you study undergraduate, study physics, and then you do what you want. And so I studied physics as an undergraduate and then just followed my nose. I mean, nothing dramatic, no eureka moments or anything like that. And I enjoy the humanities, and I went to a school in Texas, Southern Methodist University. I don't know who's ever heard of it, but it's quite a decent place. And what was really good was the humanities. The physics was bad. Not bad, but just not advanced. And I had wonderful courses in philosophy, a year's course in English novel, a year's course in American novel. And I'll never forget those things. Those are of great value. And I do think I'm not so happy to see undergraduate education move towards being job training. But maybe society can't afford it anymore. But I feel very lucky that most of my studies, or more than half of them, had nothing to do with my future career. But then I think enriched one in ways that are a little hard to quantify. And I believe in all universities, like mine at University of Chicago, we have core course. And I think that's more important than the specific courses in sciences or mathematics or things like that. Every intellectual should have a grounding in humanity.
Well, he mentions the University of Chicago, where he did a lot of his early work. I believe they have 87 Nobel Prize winners and one Heisman Trophy winner.
Maybe the universities are competing with one another, although I don't think my University of Chicago has given up on the basic notion that you need this humanities core of studies. That's part of undergraduate education. It's a loss for society, but maybe it's a price we have to pay to broaden education to more people.
As a graduate student, Cronin entered the world of particle physics at a time when it was just emerging, and that indeed was the golden era of particle physics, and the University of Chicago was probably the center of the academic world in that respect.
I think that department at the time, I was there from 51 to 55, and there was Enrico Fermi, there was Murray Gell-Mann, there was Marvin Goldberger, there was Edward Teller, there was Gregor Wenzel, there was Maria Mayer, great chemists, Joe Mayer, Harold Urey. It was Willard Libby. It was extraordinary. Although when I went there, I probably didn't appreciate as much as I do now how really extraordinary it was. Chicago it had just come off from being probably the most important place.
Here he talks a little bit about a couple of the legendary figures that were there when he was studying.
Fermi was very, warm and friendly and not intimidating at all, but I was scared to death of him. The person I thought was the warmest, although he doesn't have a reputation now, was Murray Gell-Mann. He was very open to students, and I had a couple classes with him. And he's become a little difficult type person now, but he was just marvelous. And there were some people. Fermi died in 1954, and the people who were with him who didn't leave. I mean, everybody I mentioned almost left between, say, 54 and 58 or something like that. And the people who remain, and the reason I say that is I went back to Chicago in 1970, were not as strong. I did a thesis on nuclear physics, and I selected my sponsor more because he was a kind man than the field. I was pretty shy then and quite frightened by these great figures. So I worked with a fellow named Samuel K. Allison. But then when I finished, there were wonderful opportunities in particle physics. And I went to Brookhaven National Laboratory, where the first machine that could make heavy unstable particles was running. It was called the Cosmotron. It was a 3 GeV machine.
Here he goes into the genesis of the experiment that ultimately won the Nobel Prize, and he talks about the history behind it.
The experiment that was awarded the Nobel Prize was four people, and pretty simple. I mean, as things go, and we built all the electronics ourselves, and built the spark chambers ourselves, and so one was very close to the apparatus. But nature was simpler. There were so many questions to address, and it was relatively easy to do it. You didn't need casts of thousands. It was performed in '63. And but we didn't publish till about a year later of the CP part of it, the violation part. There were other things we measured. In fact, the experiment was not designed specifically to look for a violation of CP. It was designed to look for some other phenomenon that another physicist, creative physicist, had claimed. And because of this is very important, new developments in technology permit you to do things you could never dream of before. That continues all along. So we could do a beautiful job in checking this crazy theory of this guy, but at the same time pushing the limits on this forbidden decay of the K long by a factor of 100 from where it was done easily. But we found, we were surprised that there were events that we didn't expect.
Here he talks about the genesis of the work by Murray Gell-Mann and one critical question asked by Enrico Fermi.
It really began with Murray Gell-Mann, who was at Chicago, and he was the first taking cosmic ray data to try to make a systematic understanding of the properties of these new unstable particles, the K-mesons, the lambdas, the sigmas, cascades, etc. And he got it completely right. So Fermi was in this class, and he asked the question of Gell-Mann, if they can both decay to the same final state or final set of particles, how are they different? Gell-Mann in later times says, well, he understood the question, answered it, but it was clear it stimulated a paper by Gell-Mann and Abraham Pais in which there was a prediction not only of a short-lived neutral K-meson, but a long-lived K-meson. And that was just brilliant. And it's the kind of physics where an experimentalist can understand it, and it gives you shivers, just like a beautiful piece of music. I mean, it was just marvelous. We were able to measure the limit 100 times better than what had been reported in the cloud chambers. And we actually found events, which was a complete surprise. So it's not that we set out to test it. I mean, we knew to test it. We had no expectation we'd see anything other than nothing. But there was no eureka moment. It oozes into existence. Because if you're measuring the picture by picture by picture, and you put the stuff in the computer, and finally you see this bump appearing where one did not expect it.
Another person who was critical to the development of their work was the great Russian physicist Andrei Sakharov.
I remember at the time I had some sense that this had to do with space and time, was probably pretty fundamental, but it was Andrei Sakharov in 1967 who wrote an explicit paper just with the ideas of having this matter-antimatter asymmetry, instability of the nucleon, and thermal non-equilibrium. Those three things together, he put together kind of a scenario of how you could have a Big Bang and emerge with matter only by having 10 to the ninth of the particles annihilate with one another, and the 1 10 to the ninth left, 10 to the minus ninth left is us. It is amazing that you make these measurements with this not too beautifully designed equipment, not working very well, in a hot and dusty environment, and yet it has these profound consequences. It's amazing. So we knew it was important. I mean, just in the context of particle physics, never mind the cosmology. But the cosmology certainly was made it far, far more significant. Sakharov, 3 years later, made his predictions. And then in maybe 1978, 1979, a number of people started writing about the relationship of this violation with the Big Bang, because the Big Bang wasn't all that sharp, and cosmology and the discussion of cosmology was just coming up and further developed. So I think around 1978 or something like that, a number of papers were written about this, of which then the matter-antimatter asymmetry played an important role.
Finally, Cronin answers the question that a lot of the Nobel Prize winners are asked, and we play on this podcast: what did winning the Nobel Prize mean to him? He won it relatively late in life. He won it at 50, and here he explains the importance that it held. And basically his answer is not too different than a lot of the other Nobel Prize winners. People answer your phone calls after you won the Nobel Prize.
Of course, I was 50 years old, and I think I was mature enough not to be carried away, and it is of some use. I mean, 10, 15 years later, I began to organize an international conference and international collaboration on cosmic rays. And we needed access to politicians, and the Nobel Prize is perfect for that. So it was very useful for that.
Well, I'm going to close on that note. I want to thank my producer and IT genius, Sid Tepps. You know, it's hard coming up with closing songs for these particle physicists. For Val Fitch, I used a matter song. I used Buddy Holly's It Doesn't Matter Anymore. And there aren't that many matter songs out there. But there is one other good matter song out there, and it was done by one of the first groups signed to the Beatles record label, Apple. In fact, many people thought that this was the Beatles singing it when they first heard it in 1970. And Pete Ham, the leader of the group, was actually using George Harrison's guitar. In 2001, the Gap wanted to use this song in a commercial, but Apple Records, which owns the right to it, asked for a lot of money, and the Gap was turned down. Anyway, the group here is Badfinger. Badfinger was a great group with a very tragic story, but I guess that's a tale for another day. So in tribute to the particle physicist James Cronin, here is No Matter What by Badfinger.
No matter what you are, I will always be with you. Doesn't matter what you do, girl, I'll go with you. No matter what you do, I will always be around. Won't you tell me what you